Benicia, a waterside city in Solano County, California, located in the North Bay region of the San Francisco Bay Area. Benicia is known for its small town charm, history, and high quality of life. It consists of approximately 12,000 households, which house nearly 27,000 residents. Benicia is very well known for its downtown waterfront, which has about 200,000 square feet of commercial and office space, which consists of various local businesses, shops, and restaurants. Benicia's industrial park is home to over 600 firms employing more than 5,000 workers, which comprises over a third of total jobs in Benicia. The city of Benicia, a cornerstone of energy from petrochemical to electrical production. Limitations to Benicia distribution grid, a challenge to electrification and emission reduction goals. This presentation is brought to you by Danny Zepeda and Ronaldo Souza, Energy Systems Management grad students in Environmental Climate Change Mitigation class. We aim to highlight the limitations of Benicia's power distribution grid and how it poses challenges to achieving electrification and emission reduction goals. Our objective is to demonstrate that climate change strategies, emission reductions, and electrification must consider the electrical distribution circuit level. Benicia has taken steps to combat climate change by setting emission reduction targets, developing climate action plans and strategies, and calculating emissions inventory. As with many other cities, Benicia's climate action plan includes electrification, which can exceed the current electrical distribution system capacity, particularly residential and vehicle electrification. We emphasize the need to consider the distribution grid when devising climate mitigation and electrification strategy. Although there has been significant investments in decarbonizing generation and upgrading transmission infrastructure, the distribution system has received less attention. This system is closest to the homes targeted by the most electrification strategies. Identifying the available capacity for electrification can help estimate the amount of emissions that can be reduced. We approach this in 5 steps: understanding the system, including substation and distribution circuit level, identifying limitation of existing circuit, such as loading, summer peaks, and rated capacity, forecasting the maximum possible electrification load for EV and residential electrification scenarios. Using the electrification forecasted demand, we can calculate possible emissions avoided. After understanding circuit electrification and emission reduction capability, we can look to develop solutions to meet the set emission reduction goals. To understand the electrical system in Benicia, we use the PG&E Integration Capacity Analysis Map, which provides information on transmission, substation, and distribution circuit, including limitations, loading, peak limits, and customer demographic. Our analysis revealed that the city is served by 2 major substations: the Bahia substation, which has a 230 kV incoming transmission level and a nominal circuit level of 12,000 volts, and has powered 5 distribution circuits that supply majority of the city; and North Tower, located in Glen Cove, Vallejo, which has a 115 kV incoming transmission line and a nominal circuit level of 12,000 volts. There are 2 distribution circuits from this substation that are shared between Vallejo and Benicia. Using the PG&E Integrated Capacity Analysis Map, we identify each circuit, extract the customer demographic quantities, and examine the summer peak load. For this project, we focus on Circuit 1101, which has the highest residential count and is 75% loaded. While we consider North Tower 1104 and 1108, those circuits are shared with the city of Vallejo. To simplify our analysis, we use Bahia Circuit 1101. The PG&E Integrated Analysis Map provided a load profile for the circuit. As we plan to forecast electrification that includes heating during the winter, we had considered both summer and winter peak. Our analysis show that summer peak consumes approximately 70% of the circuit capacity, while winter peak uses about 50% of the capacity. Now, I'll turn it over to Ronaldo to discuss possible electrification forecasts for line 1101.
So, to forecast possible electrification for circuit 1101, we assume that EV would add 7.2 kW using level 2 charging at home. And for residential electrification, replacing the water heater with electric would add 1 kW in the summer and the winter peaks. And replacing the gas heater with electric would add 20 kW for a winter peak. To consider the combined impact, 2 scenarios for summer and winter peak were developed. In the winter peak case, for example, the current infrastructure is capable of supporting an increase of 3 megawatts, which accounts for 423 EVs, and 2.8 megawatt, which accounts for 131 homes electrified without overloading the circuit during the season. So, what does this mean in terms of rate adoption? In summary, the 423 EVs represent 5% of EV adoption, and the 131 electrified households represent 3% of household electrification without overloading the circuit during the winter peak. Knowing the maximum EV and residential electrification load, it's possible to estimate the potential greenhouse gas emissions reduction. We assume that each household would avoid an average of 6.5 tons of CO2, 4.5 tons of CO2 per vehicle, and around 2 tons of CO2 per home. Calculations show that the Circuit 1101 is capable of reducing emissions by 5%. This is a tiny proportion for the size of the planned challenge, which is to reduce its emissions by up to 80% by 2050, based on the 2005 baseline, estimated at around 8.7 megatons of CO2. Therefore, understanding the infrastructure limitations are important to develop solutions to achieve climate goals. For Bahia Circuit 1101, we developed 3 scenarios. For scenario A, which assumes that highest EV adoption, 80%, and the lowest building electrification, 47%, required less infrastructure than scenario B, which assumes 75% EV and 70% building electrification adoption. Scenario A requires 97 megawatt and scenario B 114 megawatt. On the other hand, scenario C, which assumes less EV adoption, 70%, requires much more infrastructure to accommodate EV and building electrification. It requires 124 megawatt. 2 important points can be taken from these results. First, more EV adoption will require less building electrification adoption to achieve climate goals. Secondly, greenhouse gas emission reduction goals in these sectors will require a minimum of 8 times more distributed energy infrastructure. According to our analysis, scenario A is the most economic path, and upgrading its system will cost around $174 million, including the substation and the circuit upgrades. Another solution to reducing emissions is to control the coinciding peak, which is measure of customers' contribution to the system's overall peak demand. Minimizing these peaks requires offsetting the usage time of electricity to not overload the circuit. This either will require leveling out the electrical load. For example, EV charging at night when the electrical demand is low. This will save on building more electrical infrastructure and help increase CO2 emissions reduction levels. Now, we will come back with Benicia that will review other solutions to climate goals.
Okay, so there are several solutions that can be considered to prevent overloading of the distribution system and reduce greenhouse gas emissions. One way is to upgrade old electrical appliances to more efficient loads to reduce the load on the system. The city can also continue promoting energy conservation practices such as walking or biking to work or stores. Working with local refineries to provide cleaner fuel options like hydrogen renewable gasoline or diesel can also help reduce emissions. Policy can be implemented to prevent overloading the grid during summer and winter peaks period. The city can continue promoting developing more public transportation options to reduce travel miles. New technologies such as smart grids or energy management systems can help conserve energy and save money. Exploring distribution energy resource technology and microgrid applications can also help remove load from the distribution circuit. In conclusion, while electrification has limitations and challenges in meeting greenhouse gas emissions reduction goals, it is important to consider the distribution system when implementing emission reduction strategies. We recommend that the City of Benicia conduct a detailed study to identify circuit limitations, calculate potential greenhouse gas emissions avoided with electrification, and identify upgrades to increase carbon reduction efforts. It is also important to work with utilities to prepare realistic infrastructure upgrades and consider alternative solutions to meet reduction goals and reduce reliance on electrification. Thank you.